Dr. R. Hemavati is an assistant professor in mathematics in Queen Mary's, Chennai. She has specialized on functional analysis. Having 12 years of experience in teaching, she has won various awards for her performance. She has published papers in 14 international journals, 3 national journals, and has presented papers in 10 international and in 5 national conferences. She is also one of the editors for an international journal.
Welcome to UGC lecture series. In the earlier sessions, we were talking about test of significance. Large sample test and small sample test have been discussed. In large sample test, we have seen Z test for mean, Z test for proportion and Z test for standard deviations. In small sample test, we have discussed T test for mean. In continuance with the small sample test, in this session, we will be discussing about F test and chi-square test. F test is for testing difference of variances. Hence, the objective of this session is to work out some problems in small sample test, F test, for testing the difference of variances, and chi-square test for testing single variance. So far, if you take Z test will be the only test for testing difference of means as well as for single mean. In T test is the small sample test for testing single mean and difference of means. Whereas with respect to variance, chi-square test will be used for testing single variance, whereas F test will be used for testing difference of variances. So, that will be discussed. So, F test for difference of variance, this tabulated values already given at 5% level significance separately and at 1% significance level separately. So, after working out 28 examples in test of significance and sampling distributions, this is the next example. Let us see how this problem is worked out. The data given below relate to 2 random samples of employees from 2 different states. Test the hypothesis that variances of the populations are equal. The data given is with respect to 2 states, state 1 and state 2. So, the mean is 28 and 19 for state 1 and state 2 respectively, whereas the variance is for 40 and 42 respectively. Sizes are 16 and 25. Let us work out the solution for this. Now, taking sample 1 as a state 1 values, x1 bar is 28 and sample 2 is state 2 values, x2 bar is equal to 19. And the variance for sample 1 is S1 square. S1 stands for sample standard deviation, whereas S1 square will be sample variance. So, S1 square is equal to 40 and S2 square is 42. Size N1 is equal to 16 and N2 is equal to 25. With this, we proceed to find out the F value after discussing the usual procedure of testing of significance. Okay. What is step 1? Step 1 is actually setting up null hypothesis. Step 2 is setting up alternative hypothesis. Step 3 level of significance, and step 4 is computation part, and step 5 is comparison and conclusion part. So, step 1 is setting up of H naught, where in H naught we fix up the population variance. What is the population variance value given in the question? Step 1 is mentioning that 2 population variances are equal. So, H naught says sigma 1 square is equal to sigma 2 square, that is 2 population variances are equal. That is what is sigma 1 square is equal to sigma 2 square. Next, step 2 is nothing is specified in the question about a one-tailed alternative, mentioning that test whether one population variance is greater or lesser than another population variance. Therefore, here we mention the H1 as a sigma 1 square is not equal to sigma 2 square, exactly complementary statement of H naught. That is 2 population variances are not equal, or not equal. Step 3 is level of significance. LOS, level of significance, is 5%. If it is not mentioned, let us take it as 5%. And degrees of freedom, at present we cannot find out because it is based on the F computation. F value is whether capital S1 square by capital S2 square or capital S2 square by capital S1 square. Step 4 is the actual computation part. Capital F is equal to S1 square by S2 square according to whichever is greater, that will come in the numerator. S1 square by S2 square or S2 square by S1 square, where capital S1 square is the estimate of population variance, that is n1 small s1 square by n1 minus 1, and S2 square is n2 S2 square by n2 minus 1. What are the n1 s1 square values which we have written with the starting of this problem? n1 is 16 and s1 square is 40. x1 bar is an information which is irrelevant to this problem. We need only n1 and s1 square. So, n1 is 16 and s1 square directly is 40. You need not square 40 again, it is a squared value, and then 16 minus 1, which is equal to, this value comes to be equal to 42.667. And similarly, n2 s2 square by n2 minus 1 is 25 into 42 by 25 minus 1, which is equal to 43.75. Now, when you see S2 square is greater than S1 square. So, the formula of F applies as S2 square by S1 square, 43.75 divided by 42.667. Since the F formula stands for greater variance by smaller variance, always F value will be greater than or equal to 1. Okay. So, this particular computation gives you the value 1.0253. Now, we have come to the comparison and conclusion part, where we can say that calculated F at 5% level of significance, comma, the degrees of freedom. Now, we have to take it from step 3. Since the formula is S2 square by S1 square, degrees of freedom formula will be N2 minus 1, comma, N1 minus 1. N2 is actually 25. So, 25 minus 1, comma, 16 minus 1, which is equal to 24, comma, 15. So, the calculated value of F at 5%, comma, 24, comma, 15 degrees of freedom. Here the degrees of freedom is a pair, degrees of freedom for numerator and degrees of freedom for denominator. So, this is the calculated value of F at 5% level of significance, comma, 24, comma, 15 degrees of freedom. The value which you just calculated is 1.0253. Okay. And tabulated F at 5%, comma, 24, comma, 15 degrees of freedom. This you have to take the value from the tables. Just refer the tables. Actually, 20 values are not directly available for the numerator. 24 is not directly available. We will take 25 for the corresponding degrees of freedom, right. So, what is the degrees of freedom? 24. 20, since 24 is not, after 20 we have directly 25. Since 24 is not available, we are taking 25 and corresponding 15 degrees of freedom, that is 2.28, this value. Our tabulated value is 2.28. Now, comparing the calculated value and tabulated value, 1.0253 is lesser than 2.28, therefore, H naught is accepted. So, we write calculated value modulus is less than tabulated value, therefore, H naught is accepted, which means two population variances, that is variance of first population and variance of second population are equal. This is our conclusion. You have been asked to test whether two population variances, test the hypothesis that variance of the population are equal, and answer to this question is yes, variances of the populations are equal. Now, let us see this example where the values are not directly given to you. You have to calculate the values, usual computation. Two horses A and B were tested according to the time in seconds to sum a particular track with the following results. Horse A in track 1 gives you 28 seconds and then 30 seconds in track B like that, and 32, 33, again 33, 29 and 34. Horse B gives you the values 29, 30, again 30, 24, 27 and 29. Analyze completely in and as many ways as you can the above data and state whether you can discriminate or not between the two horses. That is, you are asked to test whether the two horses are varying or not. Discriminant stands for variability, and if so, with what degree of confidence. That is, it is based on the level of significance you fix up. If we fix up level of significance as 5%, we can say our conclusion is 95% confidence. And then if you fix up the level of significance as 1%, whatever the result comes as conclusion will be a 99% confident result. Let us work out this example. So, first of all, testing the discriminancy of the two horses, horse A and horse B, we have to use F test for difference of variance, because two types of horses have been given, horse A and horse B. So, we will use the F test. Going ahead with the usual step of procedures. Step 1, H naught says sigma 1 square is equal to sigma 2 square, that is the two horses are not discriminant, they do not vary, they are equal. Two horses do not discriminate. Okay. They do not vary according to H naught, that is null hypothesis. Then H1 says sigma 1 square is not equal to sigma 2 square, in the sense two horses discriminate themselves. Okay. Step 3, let us fix up the level of significance as 1% and degrees of freedom at present we cannot just find out. And then step 4 is the calculation part, where we have to calculate F is S1 square by S2 square or S2 square by S1 square, where S1 square is equal to summation x1 minus x1 bar whole square by n1 minus 1, and S2 square is equal to summation x2 minus x2 bar whole square by n2 minus 1. We have to calculate these summation values and substitute in S1 square and S2 square and see whichever is greater, and accordingly calculate F value. Okay. So, these are x1 values, x1. So, summation x1 stands for adding these values, summation x1 is equal to 219. So, x1 bar is summation x1 by n1, and 219 by how many values are there? 7 values. So, 219 by 7, which is equal to 31.28. So, each value is subtracted with 31.28, which is this is x1 minus x1 bar, which is actually each value is subtracted with 31.28. Okay. So, 28 minus 31.28 gives you minus 3.28. Similarly, 30 minus 31.28 is minus 1.28. Like that, these values are calculated. Okay. And then this particular value is x1 minus x1 bar whole square. This is the square of these values. Minus 3.28 whole square is 10.7584. Like that, this particular column is being formed. Then this is x2 and this is x2 minus x2 bar, and this is you can use small itself x2 minus x2 bar whole square. Like we have calculated for x1, we have to calculate for x2 also, where summation x2 here gives you 169. So, that x2 bar is summation x2 by n2 is equal to 169 by how many values are there? 6 values, which is equal to 28.16. Okay. So, each value is subtracted with 28.16. So, x2 minus 28.16, and these are its square values 0.84 whole square. Okay. And the summation here comes to be equal to summation x1 minus x1 bar whole square is equal to 31.429 or 88, and similarly this value is x2 minus x2 bar whole square, this summation values is equal to 26.8336. Okay. Now, taking these values, we shall calculate capital S1 square and capital S2 square. Capital S1 square is equal to 31.4288 or 9 by N1 is 7 minus 1, which is equal to 31.429 by 6 is equal to 5.238. Similarly, x2 minus x2 bar whole square divided by n2 minus 1 is 26.8336 by 6 minus 1, which is 23.8336 by 5. This value is 5.3667. Now, we shall calculate f, which is greater actually 5.238 or 5.3667. Actually 5.3667 is greater, therefore, f is the formula is S2 square by S1 square, which is 5.3667 by 5.238. This value is 1.0245. This is your calculated f. Now, the degrees of freedom has to be decided now. Degrees of freedom is again n2 minus 1 comma n1 minus 1. N2 is 6 minus 1 comma 7 minus 1 is 5 comma 6. Okay. Now, we have come to the comparison step where calculated f is written as 1% comma degrees of freedom is 5 comma 6, which is equal to 1.0245. Tabulated f at 1% comma 5 comma 6 degrees of freedom. We have to refer the tables. Unlike in t test, f and 1% level of significance values will not be given in the same table. There is a separate table for 5% significance level and 1% significance level. Now, this is the table for 1% level of significance, where you have degrees of freedom is 5 for the numerator and 6 for the denominator. This is for 1% significance level. We have degrees of freedom 5 and then 6, this is 8.75. Now, our calculated value is much lesser to the tabulated value. Therefore, step 5 is a calculated value is lesser than tabulated value. Therefore, H naught is accepted, which means 2 horses, the ultimate inference for this problem is 2 horses do not discriminate. Okay, that is the conclusion. Now, after discussing the F test for difference of variances, now this is for single variance. Therefore, the sample variance has to be discussed now. Let x be the population random variable with mean mu and standard deviation sigma. We assume that random sample spaces of sizes n are taken with replacement, or if they are taken without replacement. We assume that population size is much larger than n. That is, if you take the sample with replacement, then sample size is enough, of n is enough, where we are not bothered about the population size. But if you are taking the sample without replacement, that is, after the sampling process is done, the items are not replaced for the next process of sampling. So, in that case your sample space will be decreasing according to the number of items taken. Therefore, the population size has to be taken into account, and in that case population sizes should be much larger than n, so that the whole population is considered to be normally distributed. Then the values x1, x2, etc. up to xn. Since we are taking the sample of size n, therefore, there will be n values of x in a random sample, or in effect values of n independent random variables, capital X1, X2, etc. up to xn, each with mean, mu and standard deviation sigma. Now, the random variable capital S square is equal to this is what is summation xi minus x bar whole square divided by n minus 1, okay, where x bar is the sample mean is called, this particular capital S square is called sample variance. Now, how does chi-square distribution comes into the picture when we are discussing about the sample variance? So, chi-square distribution is derived from the samples having single variances. Okay. Suppose x is a random variable with mean, mu and variance sigma square, and let x1, x2, etc. up to xk be random sample of size k corresponding to x. Then since each random samples can be approximated to a standard normal distribution, the corresponding conversion of x to z is z1, z2, etc. up to zk be k independent normal variables, each with mean 0 and standard deviation 1. This mean 0 and standard deviation 1 is the mean and standard deviation of this particular z values. Then the random variable chi square is, this is called chi square, is equal to z1 square plus z2 square plus etc. zk square is called a chi square random variable with k degrees of freedom. This is according to the random sample size. Now, where each zi is written as xi minus mu divided by sigma. This is the usual conversion of xi values to standard normal distribution. Now, chi-square test is used for the hypothesis testing of a single variance. What is the procedure? The procedure is first of all we have to fix up h naught, that is your step 1. H naught is fixed up as sigma square value. Whatever the population variance value is there, that has to be fixed in step 1. Step 2 is sigma square is against the h naught, where h1 states that sigma square is not equal to the particular value, or sigma square is greater than a particular value, or we say that sigma square is less than a particular value. In this case it is two-tailed test, and in these two cases it is one-tailed test. Then as usual step 3 is level of significance part, level of significance and degrees of freedom part. The degrees of freedom is actually k minus 1 for chi-square distribution. Then step 4 is the formula part for testing a single variance is chi square is equal to n minus 1 into s square by sigma square, or chi square is equal to summation xi minus population mean is directly available, then xi minus mu whole square by sigma square, where I ranges from 1 to k. Okay, if the population mean is not mu is not available, then chi square is usual summation xi minus x bar whole square by sigma square. So, this is the procedure, and then usual step 5 is calculated f at the corresponding level is whether it is lesser than or greater than tabulated value. This you have to check, and accordingly you have to accept h naught or reject h naught, and if you are rejecting h naught, h1 is accepted. In this session some problems have been worked out in a small sample test that is F test for testing difference of variances. A problem has been worked out where the values of samples are directly given, that is the sample variance and the size are directly given. And another problem is worked out where the values are not the sample variance and the size values are not given directly, where you have to calculate capital S1 square and capital S2 square and accordingly use F formula. And then chi-square test is also discussed, the procedure for chi-square test and the derivation of a chi-square distribution from for testing single variance has been discussed. Based on this discussion in this session, the questions are posed like this. Given two independent samples from normal populations, test whether the variances are equal at 5% level. Sample 1 values are given as 3, 8, 10, 7, 4, 5 and 12. Sample 2 values are 5, 13, 15, 9, 7, 12, 16, 18 and 20. As discussed, it is not necessary sample 1 size should be equal to sample 2 size. So, you have to test the variances equality using F test, and then explain the procedure for test for single variance. Thank you.